Good evening, everyone, and welcome to my presentation. My name is Andrew Lee, and I'm a Master of Science candidate. And today I'll be presenting my master's thesis, which is titled Correction of Clinically Important Errors in MRI Measurement of Blood Flow, which I've been working on for the past 6 months at the Department of Anatomy of Radiology under the supervision of Associate Professors Brett Cohen and Alistair Young. So let's get right into it. So what is MRI? MRI, or magnetic resonance imaging, is a medical diagnostic imaging technique that allows clinicians to see cross-sectional slices of the human body. Perhaps you've even been inside, Perhaps you've even been inside an MRI scanner. Interestingly, we can also use MRI to measure blood flow. Now, so blood flow measurements. Blood flow measurements are very important clinically because, for example, we use blood flow measurements to assess patients undergoing cardiac surgery, as well as babies with congenital heart disease. Typically, this is done using an ultrasound technique called Doppler echocardiography. Now, MRI offers a technique called phase contrast that also allows the quantification of blood flow. And the phase contrast scan sequence produces two images. The first is a magnitude image, and the second is a phase image. In the magnitude image, you can see anatomical structures, and in the phase image, the pixel value of the phase image represents the speed at which blood is flowing at that location. And using the phase image, we can calculate interesting statistics like flow rate and cardiac output. Now, phase contrast has recently gained a lot of attention because it's actually a more accurate method than traditional methods such as Doppler echocardiography. However, we have found that there are still some problems with the phase contrast technique. Now, the main problem with phase contrast is a measurement error called background phase. This is a color-enhanced background phase contrast image measuring the flow rate inside the aorta. Interestingly, this is not the image that we get from the MRI scanner. What we actually get from the MRI scanner is this image here. And as you can see that the colors of the two images are slightly different, indicating that we're actually measuring slightly different velocities. Now, this difference or error is called the background phase. So why do we get a background phase appearing in our images? And the answer is because of eddy currents. Eddy currents are electric currents that get induced inside the scanner as a result of the scanner's rapidly changing magnetic field. It's basically the same idea behind how electric generators generate electricity. During an MRI scan, the magnetic field inside the scanner changes rapidly. It pulses up and down. And in the phase contrast scan, this waveform has to be very accurate in order to get accurate measurement results. However, because of eddy currents, this waveform actually becomes distorted. And as a result, we get a background phase appearing in our images. To give you an idea of how serious this problem is, a research group in 2010 published a paper evaluating the accuracy of MRI scanners in measuring flow rates in the aorta and main pulmonary arteries. This graph shows the measurement error of scanners made by 3 different manufacturers tested at 12 different locations. The threshold at plus or minus 0.6 shows what is the acceptable error, and as you can see, all the MRI scanners fail to meet this requirement. All the stuff that I have presented to you is stuff that we already know. I've told you that background phase is real and it's a serious problem in phase contrast MRI. So how does my research tie into the grand scheme of things? The next step would be to find a way of correcting this problem. In order to correct for background phase, we need to know the background phase image. Because if we know the background phase image, then we can just simply subtract it out and that gives you the true velocity image. However, the problem is, in all cases, we don't actually know what this is. So my research is about answering the question, well, given any image or scan sequence, what is the background phase? And interestingly, no one has actually found a solution to this problem. The way that I'm going to approach this problem is to use a mathematical modeling approach, never been done before. The idea is that we can actually describe background phase very accurately using mathematical surfaces. For example, here I'm using a two-dimensional surface to describe the spatial distribution of background phase of the image on the left. And we can extend this idea into 3, 4, or even more dimensions. The way to approach this is to first measure the background phase in all 3 dimensions of space and time. And this would involve running scans that sample the background phase at different slice orientations. We then fit this data to a model, and this would allow us to predict the background phase for any scan sequence. So how do we measure background phase? The idea is that instead of putting a patient inside the scanner, we put something called a phantom. And a phantom is a substitute for a human being. For example, this orange ball that I have made for my master's project. Now this phantom here is stationary. That means that there are no moving parts inside the phantom. So that means any non-zero velocities that we register in our phase contrast images must be purely due to background phase. The scan sequence that I used is a special eddy current scan sequence. And you can think of this as a simplified version of the more complicated phase contrast scan sequence. What the scan sequence does is that it produces a single step change in the scanner's magnetic field. Now this step change in the scanner's magnetic field deliberately induces eddy currents, which therefore induces a background phase. And we can measure this background phase at different instances in time and fit a curve to it that would allow us to predict the background phase in the time dimension. Now, the reason for doing this is because of the idea that any scan sequence is really a whole bunch of step changes. So if we can describe the background phase for a single step change, then we can just use superposition to find the resultant background phase for any scan sequence. Of course, the output of the scan is an image, so we also get spatial information. After about 40 hours of scanning and processing using some software that I've written, I was able to produce this animation, which shows the background phase as a result of a single step change in the scanner's magnetic field at one slice orientation, and how it changes in the spatial and time dimensions. The more interesting features of this animation is its variation in the time dimension. So for example, if we take this point here and plot its value in the time dimension, we get this graph, which shows that background phase actually decays with time. And we would expect this because the eddy currents responsible for background phase should also decay with time due to the resistance of the scanner's conductive housing. However, a more interesting or perhaps concerning observation is that when we repeated the exact same experiment on a different day, we actually get different results. And this seems to suggest that background phase varies in time in the long-term sense, which if true would be a major limitation to this method, because then that means we wouldn't be able to predict it anymore. We think that this may be due to temperature fluctuations inside the scanner, as background phase is also sensitive to temperature. However, the reason why the two results are inconsistent remains work of ongoing research. So in summary, I've told you that phase contrast is a highly accurate method for quantifying flow, provided we fix the background phase problem. Current research shows that background phase is caused by unintentionally induced eddy currents, and that background phase is the most common source of error, and it's caused by eddy currents. Now, my experiments have shown that background phase is geometrically simple, and that we can also very accurately predict it using mathematical, and the time stability is uncertain. Thank you very much.